record on this. Yeah. Okay. Hello, everybody, and welcome to our review session. As I noted earlier, a few of you guys came in a little bit afterwards. We're going to be a little bit running much shorter today than usual. We have the holiday coming up, and Shana Tova or happy Rosh Hashanah to any of our friends who are celebrating. So today what I'm going to do is it's going to be more of me learning from you guys so I know what to give back to you on Monday. All right, I'm going to cover some material as well, of course, but one thing that I really want to understand from you guys is go ahead and pull out your notes now. Go ahead and I think it's all in one PowerPoint. Take a couple minutes, take some time to slide through those concepts. By now, you should be at least familiar with what was being presented to you, okay? Now, the reason I say this is I want you to tell me what you need me to focus on, okay? Because Monday, here's what's going to happen. Today, I'm going to go through what I can. I'm going to let you guys go. I'm not going to hold you for too long, but I'll go through what I can up to about inhibitors, right? Because the inhibitors part gets a little bit, a little bit tricky. I'll let you guys focus on whatever we have up till that. Okay, and you can do your own understanding of inhibitors at home and come back to me on Monday and we'll walk through it. I'll finish up the lecture portion, right, of enzymes, and the majority of Monday is going to be drilling you with practice questions. Okay, because enzymes in particular, it's not like pH, and I mean, granted, there is equations in pH and stuff, but it's not going to be like proteins and buffer systems and equilibrium where, yes, there are equations involved, but it's largely conceptual. It's nothing like with curves and shifts and inhibitors that change the different intersections and all that. This gets a little bit granular. Okay, so I'm not going to sit here and waste your time babbling on about a slide that all you need to do is read it, or that Dr. Peterson, like it was extremely clear. There's no way you don't understand what she said. I'm gonna breeze through that. Okay, what I want to do is prepare you for this exam. Okay, you don't want to hear the same lecture twice. Granted, yeah, it's good to get different perspectives, but no, what I want to do is show you, okay, here's a question. Go ahead, try to answer it. You have a minute because time matters, right? We can't be sitting there all day long. You got a short amount of time. Try to answer that. Okay, time's up. Let me try to explain this to you guys, step by step by step by step. How should you think about this problem? What should come to your mind when you see these key words, right? I want to get you ready for the exam. I don't want to spend time reiterating what Dr. Peterson already eloquently expressed to you guys. Now, I hope you guys are taking out your notes now and scrolling through. Put them in the chat. Put into the chat what you really think. Like if it's not clicking with you immediately in your head right now, if you're not like comfortable with whatever you're seeing on that slide, put it in the chat. Okay, because I'm not going to go through things that you guys don't mention. I don't want to waste your time. Is there anything from enzymes in particular that you want me to really just jump into on Monday? Competitive, yeah, exactly. So competitive, uncompetitive, non-competitive examples. That's a tricky one. That took me some time as well when I was in the class. So we will definitely be running through a bunch of examples there. I want you guys super familiar with that. So absolutely, I will be going through that. Bacteria mimicking the beta-lactam antibiotic, which gives resistance, but I'm still confused. Okay, yeah, so I'll definitely run through that as well. I'm not sure how testable that's gonna be on the exam, but I'll check in with Dr. Peterson just to get a better idea of how in depth she wants me to go, because that can get also a little bit intense. What else do we got here? Or maybe I'm totally wrong. Okay, yeah, so I'll definitely keep this chat so we can I'll confirm with Dr. Peterson, and and I'll also ask her what is going to be what she thinks I should really focus on, especially. So we're making the most use of our time. Allosteric enzymes. Okay, we'll definitely do that. Ternary structures, graphs versus inhibition graphs plus ternary complex. Okay, so we're going to talk a little bit about ternary complex today. We're not going to do too much practice questions today, but I will step, I will mention ternary complexes and, definitely get a bit more in depth when we do the explanations. Like, again, these practice problems are everything. Enzymatic kinetics in general, yeah, well, yeah, so that's definitely going to be important. Okay, implications of 2,3 is phosphoglycerate and the O2 dissociation curve. Okay, this is good, guys, keep them coming. Didn't fully understand the conditions that move the different curves either left or right. Important, yes, we're definitely going to have to get through that. Okay, thank you, Allison. I'll give you guys a little bit more time. Keep going through. Tell me what.
Uh,
Yes,
can I
Belinda,
say it?
please.
Hi. Uh, can can you also go over the curve with like a person having sickle cell and the
Mm,
carbon monoxide one?
definitely, absolutely. You can. You're probably going to see something on the exam with that as well. Dr. Peterson is also really uh, helpful with these type of problems because she introduces pathology, which I love. It kind of makes it hit home a little bit differently. So I'll definitely bring that up. If you see some pathologically oriented questions, take a good look at those because they're likely to come up. Like if you're like the O2 curves and dissociation shifts and all that, very important. Okay. Hill equation has implications. Not sure if that's earlier. No, it was not. I will definitely be sure to mention that. Thank you, Anna. Okay. Okay. Well, if anything else does come up, specifically the graphs, yeah. So that's going to be a big one. The graphs of the different inhibitors, non-competitive, uncompetitive, and competitive inhibitors. Yeah, that's going to be a big one. So we're going to spend some time on that. That's why I'm stopping at inhibitors today, because that's a whole different beast that we're going to have to tackle. I really want to think about how to word this to you guys in a way that is most graspable. Was still somewhat confused on getting the sequence in one letter abbreviations given the full sequence. Oh, okay. All right. Sure. So I'll try to reiterate what Dr. Peterson mentioned in the Tuesday lecture when she did the whole peanut butter thing. Is that what you're talking about? Like with the yeah, the charges. Okay. Yeah, that'll be definitely be a test question. So also with regard to the problem set, um don't ask me to specifically answer the problem set question, because that's for you guys. And it's important that you guys are able to work on that on your own and submit what you have. But if there's a question that, on the problem set that gave you trouble, I am happy to give you a similar example and to run through the conceptual aspects of that to help you work your way through the question. I don't think I should be giving you guys the whole answer straight up. Otherwise, what's the point of you guys doing it? So and fortunately your assignment has been pushed back, so you don't have to submit that till Tuesday at I think at 4. Correct me if I'm wrong, but that means on Monday I can help with that, right? So I can help you, kind of focus on certain questions. I do ask though that you let me know ahead of time, preferably before Sunday, like the end of Sunday, just so that I can include them into the presentation and speak intelligently on them. All right. I don't want to have to mention one thing and then have to come back later. I want to kind of keep it ordered and structured to keep everything followable. That makes sense? Good. Okay. Can you explain the half charges? Absolutely. So yeah, so this is a lot of stuff that we saw in the earlier lectures. So I may have David also just jump on and help as well because he has a very strong grasp on these things. I think David has a nice little review sheet for you guys in the works as well. So we'll definitely get back to you with as many resources as we can to help. All right. So in the interest of time, I'm not gonna keep on answering these directly, but please, yes, keep putting things in the chat. Just let me know, like, oh, if on Monday, please also mention, just so I can go through later and make a little list of what needs to be done. Is this working for you guys? Are you guys all right with this type of format, or would you prefer that I actually go through slide by slide by slide and lecture more? Because I know personally, practice problems were the key for me. That's what made me really realize, like, oh, I actually don't know this. I better go back. But if you guys prefer, I'm here for you. You think this format is great? This format is better? Yeah, this is good. All right, bada bing, bada boom. I love it. We're doing good. Wicked better. See, oh my goodness. Whoa. All right, David, what do you think? I think that we will go with this format then. Yeah.
Yeah, sounds good. Yeah, just like submit questions like definitely before lecture so that we have a chance to work on it beforehand, just so we're clear on what we're saying. We don't want to give everyone the wrong information, but like yeah, just like reach out before, and then we'll work through it. Also, like we're free like not just during the review sessions. We're free during the week, so if you want to meet like one-on-one or like in person, whatever works for you, just reach out.
For sure. And even like I had a couple students reach out before the session, right before the session, asking questions about a few things from earlier, that I'm not going to be covering today. I'm going to make them a document. I'm going to make them a little document, a comprehensive outline explaining to them as well as I can. Okay, this is the answer to your question and why. Like I'm going to distribute that to them, and of course I'm going to include that information in the presentation as well for everyone else to see. But don't be afraid to ask questions. That's why we're here. All right, so I'm not gonna keep on addressing these, but thank you everyone for your input. I think this is going to make for a much more effective session moving forward, and really get you ready to clutch that A when we sit for the exam. And one quick thing, actually, I'll mention that at the end. All right. So let me get this set up over here on the iPad. Just give me a moment. By now, I'm technologically challenged, so just bear with me. Okay. Turn this off. Keep it there, and I'm going to jump onto here. Okay, cool. Let me make sure this works. I think this is going to make life a little easier for all of us. Yes, it does work. Beautiful. Okay, great. So let me just start off with the fact that Dr. Peterson mentioned the importance of enzyme kinetics in medicine. I can't underscore that enough. Indeed, it is extremely important, not just in medicine, but basically any science. Like I said, every section moving forward is going to involve an enzyme of some kind. These Km values and Vmaxes, yeah, they matter. You can bet, because when they told me that you're going to need this for pharmacology, I'm like, oh, pharmacology, that's a million years away. Well, I'm in pharmacology now, right? And I can tell you firsthand that the pharmacokinetics is absolutely key. In other words, if you don't understand pharmacokinetics by the time you step into class on day one of pharm, you're in for a rough semester. We did not even get a single slide on enzyme kinetics during pharm because it was assumed that it's second nature to us by now, having taken biochem. So anyone here with ambitions of med school, PA school, dental school, doing research, in the lab, whatever your ambitions may be, I'm willing to put money on the fact that you're going to have to know these enzyme slides. So do yourself a favor, learn this well. Learn it as well as you can, because you're going to make your life a whole lot easier in year 2, regardless of what classes you're taking. Again, like I said, by now, assuming you attended lecture, you know that this section, enzymes, while still very important conceptually, is a lot more in terms of graphs, curves, and equations. Quite a few people are talking about the inhibition curves, which I'm gonna hold off on today. We're gonna talk more about that On Monday, I'll send out very clear information about when and the link to that, because I believe Dr. Peterson has to tend to a different meeting, so I'm not going to be able to really use her link. So I'm going to have to, try to figure out if I can get Zoom Pro on my own, or we might have to, it might go cut out at 40 minutes, and then we have to restart, but I'm going to do my best to get access to Zoom Pro so we don't have to deal with all that mess. But I'll send that information out to all of you. But bottom line, this is one of those concepts, enzyme kinetics specifically, right? The stuff that we did before this, in terms of catalysis and acid-base catalysis and lock and key, whatever. Okay, that's all important, but it's conceptual. This part, the kinetics, the rate of the reaction, right? Inhibition. These are where concepts aren't enough. It's not going to cut it. It's a matter of repeatedly looking at practice questions and immersing yourself into the examples until you start to recognize trends. I can sit up here and lecture all day long, but until you sit and have a close look at these questions yourself and have that little inner dialogue, like, wait a minute, talking to yourself like a crazy person in the library, that's what you got to do. You got to figure this out. You got to get the wheels turning, and do it the old-fashioned way for it to really stick. Time and practice are going to help you with this exam and with enzyme kinetics in general. Some things are just conceptual. This you really do. It's a constant exposure. So do yourself a favor, get started now, and active repetition, active recall. Hit those flashcards. However it may be, Anki, Quizlet, this, whatever. I have a nice little quote that I like. Amateurs practice until they get it right, and professionals practice until they can't get it wrong. Be a professional moving forward. Yeah? Excellent. Once we get the lecture aspect out of the way, on Monday, I'm going to drill you guys with a lot of questions, so I'd appreciate it if you came in with a relatively decent understanding. Otherwise, you're going to be, just sitting around not knowing what to do when I ask you questions. All right. Any questions? I'm going to jump into the content now. Terrific. So, enzyme kinetics. Enzyme kinetics is the discipline focused on determining the rate of a reaction. This is different from thermodynamics, right? This is kinetics. This is talking about how fast is it happening. Thermodynamics is more really whether or not it will happen. Enzyme kinetics, we're assuming that the delta G is negative. We know it's going to happen at some point, but how fast is it going to happen? What under what conditions will this happen optimally, right? Think about this globally. So we know that the rate of a reaction is determined by what? What is the gonna give us like the rate of the reaction, and what regulates it? The activation energy, right? We talked about the activation energy, and this matters. I know it seems a little bit basic, but yeah, the activation energy is what's going to help determine that rate of reaction. What is the activation energy a result of? How do we know? Like what controls where the activation energy is set? It's going to be the binding energy, right? Those intermolecular or those weak interactions that we talked about in lecture 1 and during that first TA review that we spent so much time on. Those are going to stabilize the transition state of the enzymatic reaction, right? That is testable. So know these things. Know that, oh God, practicing my doctor handwriting. Don't mind me. Activation energy is going to determine the rate of the reaction. Binding energy is going to determine the activation energy. And remind me, guys, someone, what's going to give me what's going to affect the binding energy? What determines the binding energy? Well, weak interactions. And these are going to stabilize the transition state. These are very well free game, you know, because there's going to be a lot of graphs and all that, absolutely, but this is certainly a testable question, right? What's in charge of determining the rate of the reaction? And it could be any one of these, however it decides to be worded. So be familiar. Let's move on. So we know that when speaking about the rate at which a reaction is going to move, we use the term velocity. The first thing we want to consider here or in any equation is that initial velocity, right? That VO, that V0. So how fast is that enzyme going to move when it first gets going? That's what that V0 is talking about. So where we have all of our substrates still free and all of our enzyme unoccupied, right? Everything's fired up, but nothing actually connected yet. We don't have any enzyme substrate complex yet. That is our V0. That's our initial velocity, our initial rate. And that's important. But Stephen, I'm looking at the graph and the graph is curved. How am I supposed to know what the rate from these random lines is? And I know I'm kind of overlapping with a bit with what David said, but you know, considering the questions that I've gotten, it seems like we really have to kind of lock in these basic fundamental concepts before we get into things more complicated like inhibition. Okay, so bear with me. So Steve, I'm looking at the graph and the graph is curved. How am I supposed to know what the rate is for all these random lines over here? Well, if we go back to our high school math days, we learned about slope, right? Right? Rise over run. That gives us our slope. And that is going to give us that velocity at any given, well, it'll give us the velocity at any given point of time on the x-axis, right? It could be over here. It'll be the tangent. You know, that's the slope. It could be over here. It could be in all different spots. But to determine the initial velocity, which is what we're worried about right now, we're going to look over in this area where it looks almost linear toward the beginning, right? Because at this point, everything's empty. Everything's unoccupied. You want to focus over here. I know some people are still going to be a little bit confused about this concept. So think of it like in terms of when you're going to the gym and doing some bicep curls, right? You know, like you're doing some bicep curls and in the beginning, before you flex and start to lift up that weight, all your muscles are fresh, they're unused, you're pumped up, you're ready to go. So you're going to be able to move that weight a lot quicker during the first few reps, right? And then it might get a little bit slower as you go on. And especially at the end, when your muscle fibers are all being recruited and you just can't move any faster. And that's where this plateau here comes into play. Right? Or think of it, this is how I thought of it when I was taking my exam. Think of it like you're going to a restaurant, you know, and you're there right when the place opens and not too many people are there yet. And you can just go right on in through, easy peasy. You enjoy your meal, waiter's bringing your food out quick because he only has 2 or 3 tables. The day goes on though, right? And more people are coming in and the service is slowing down a bit. You're waiting 20 minutes for ketchup because that poor waiter has so many other tables and people to take care of, right? And then more people come to the restaurant and the restaurant's eventually going to have every table full and you're going to have a little bit of a line forming outside. At that point, they're working at full capacity. The staff is doing the working the hardest they can. You know, the people outside waiting in line, they'll still get seated at some point, but they're going to have to wait until somebody inside finishes up their meal and leaves before the next person can get in. That's where your Vmax is at that point. Your Vmax, that's when the maximum amount of enzyme is working and it's catalyzing the maximum amount of substrate. They're all occupied. And the only way you're gonna be able to catalyze more substrate or catalyze more reactions is by separating the enzyme from the substrate and making room for a new one to come in. I think at that point, I think that illustrates the idea pretty decently, you know. Yeah, it's all conceptually the same deal. So look at that slope over here toward the beginning of the x-axis and get an idea of the slopes relative to one another. Okay, like we have 3 different slopes here. And what do they represent? We're looking at different concentrations, right? This is 1, this is 0.5, this is 0.2. And the bottom slope, we're saying, if we look at it, it's less steep than that of the middle and the top one. Top one's the steepest. So this makes sense because more substrate is going to be interacting with the enzymes, and thus, you know, there's going to be more reactions taking place. So this top one makes sense. We have more substrate. This is going to be a little bit faster. You see that slope, how it's a little bit steeper? As opposed to this one over here, which is not as steep. This all makes sense. Okay. Let's move on. Okay, you know, let me get rid of this. I don't know what's doing up here. All right. So then we take our substrate concentration versus the velocity, and that will give us our curve. You know, always in an exam or anywhere that you're working, you know, look at these. Look at the axes. They tell you a lot. Also, look at the units. Look at the units. These are going to tell you what you're looking at. I'm looking at concentration here, millimolar, right? I'm looking at velocity here, time, amount per minute. That will give away a lot of information. Become familiar with the units, guys. So that plateau that we talked about represents the Vmax. Now, note that this graph has a little bit of a space here. Yeah, this space here is really representative of an experimental setting. Okay, experimentally in the lab, we never have perfect conditions. There are other factors that could affect the Vmax. So unless we're in a perfect lab with a perfect vacuum condition, we're never going to have what it should be. We're not going to have the expected or mathematical Vmax actually, you know, take place in a lab setting in real life. It's not going to happen. So this little space over here, that's just talking about, you know, this is supposed to show us a general experimental reaction in a lab. So if Dr. Peterson asks you, you know, what you would expect to see with a reaction with a Vmax of 2, 1.8 would be a reasonable response, right? I mean, considering the scale, right? We don't have any scale on this chart, but you know, the answer is not going to necessarily be 2, right? Because we're thinking in practical settings here. Okay. Saturation effect. Vmax is observed when virtually all the enzyme is present as the enzyme substrate complex. That's your Vmax. Okay, so if we want to increase our substrate over here, if we put more substrate in, nothing is going to happen. More substrate equals no change. Because why? Because we have all of the enzymes in their enzyme substrate complex. The waiters are busy. You're not in the restaurant yet. Why? Because it's full. Everything's full. So you cannot, it doesn't matter how you can pour 15 liters of substrate in there and it's not going to do anything. And that is responsible for that plateau. And so if we look at something else though, like this, that Km value, right? That Km value is the substrate concentration at which the enzyme is working at 1/2 the Vmax. Km is the substrate concentration at 1/2 of Vmax. Again, substrate concentration, keep these in mind. This is a substrate. This is concentration we're talking about. Units matter. Molarity. Okay, so it's important to know what these different letters are talking about. Km, we're talking about substrate concentration. The reason this matters so much, why do we care about the Km value? It tells us a lot about a reaction. It tells us about what the affinity of a substrate to its enzyme, right? And remember, there can be multiple enzymes for a particular substrate. You know, multiple enzymes can work on it, or multiple substrates for a particular enzyme. But one may be more attracted to the other than its counterpart. So let me word that better. One enzyme may be more attracted to substrate 1 than it is to substrate 2, meaning the reaction rate will be much faster in the substrate 1 enzyme complex than it will in the substrate 2 enzyme complex.
Steven, do you mind if I jump in for a second?
Please. Yeah, go right
So
ahead.
the way that I always think about Km, right? All that it means is that it's affinity, right? So forget about enzymes for a while and substrates. I always think about this stuff in terms of like magnets, right? Let's say you have like the world's strongest magnet, and then let's say you put something like a pure metal, like pure iron next to the magnet, right? No matter like how far the distance is from iron, the iron is from the magnet, that strong magnet is going to pull the iron in from like nearly an infinite distance in like half a second, right? Now, let's say you have another piece of iron, but this time it isn't so pure. It's like 50% purity, right? So at that point, okay, it'll still attract it. It just won't be as fast. So like rather than like half a second, it's going to take 10 seconds. So that's really what you're seeing with Km, right? In a perfect scenario, the binding site of the receptor or the enzyme is going to be built almost exactly for the substrate. So in that case, the substrate is going to bind to it right away. So let's say now you have, rather than one magnet, right? Now you have 10 magnets. So if all those magnets, like 5 of them are bound at one point, right? It's going to increase that shows how quickly the magnet is able to bind to iron. If that makes sense. So is that clear with everyone, or is that making a little bit more sense?
I love that example. Makes a lot of sense. Yeah, that's great.
So like to go back to the hemoglobin example from the lecture from last week with fetal hemoglobin, right? The fetal hemoglobin that's lacking the 2,3-BPG, that's like having the world's perfect magnet, and therefore you're increasing its affinity to the oxygen. Because if with normal hemoglobin that adults have, it's like having a weaker magnet. But by having a stronger magnet now, even though the oxygen remains the same, the stronger magnet is going to out magnet the weaker magnet that the adults have, meaning the hemoglobin. So therefore, the stronger the magnet, or the more affinity that the magnet, the receptor, has for the substrate, the more to the left on the curve it's going to be. Because it's saying that you need less of a purity in order to attract it, right? Because if you look at the substrate concentration, let's say like fill in random numbers. I'm going to do annotate. If I can find that.
Go ahead and share
Um,
so they can see what you're talking about.
sorry, what?
You can go ahead and share your screen if you want, just so they can get a visual.
Yeah, I'm gonna actually no, because you're recording. Let's say on the x-axis, right, in the center, you write there's a 10 millimolar concentration. If you continue going the left, right, let's say where Km is, that's going to be, let's say, 2 millimolars. So what that's saying is that because the magnet is so strong, you're working with such a pure substrate that you only need 2 millimolars of this substrate in order to get almost maximum binding. Whereas let's say the magnet was weaker, it wasn't a pure magnet, then the Km was further up at 4 millimolars, saying like, okay, the magnet is getting kind of weaker. Only at 4 millimolars of substrate does it start attracting, filling up its binding spots. Is that making sense in terms of
there's
sliding the km to the left or to the right.
I think there's a good graph as well somewhere down the line that'll demonstrate that nicely. I'm not sure which one, but yeah. So more attraction means closer to the origin, and vice versa, essentially. Yeah, well, we know that the lower the km, right? The lower the km, the higher the affinity. That's the ultimate rule here that we're trying to present to you. So if you're, yeah, exactly. All right, good. All right, thank you very much, David. That's actually a really great way of looking at it. With the magnets, absolutely. Anyone have questions on that before we move forward? Because this is important. All right, let's do it. Michaelis-Menten, yes. Now we're getting into the real stuff. Learn this equation. Learn this equation. That is important. You should know it. I'm not saying you have to know how to derive it, you know, and then that would take a whole long time. There's whole videos online about the derivation. We don't need to do that. You don't got to know that. You know, if you want to learn about it, it'll help you understand things even better. But do understand how to use it. And we'll do a lot of practice questions with this as well. It's just like our equilibrium equations from week 1. You know, knowing some of these values, right? Knowing just a couple of these values, whether, you know, if you know these 3, you can figure out your substrate concentration. You know, having these lets you algebraically work through, you know, the other components. And this whole equation that we're looking at now, this Michaelis-Menten equation, is just an algebraic representation of the curve that we just spoke about, Michaelis-Menten curve. Okay, so be familiar with this, because, you know, you might have to take some information from a curve and plug it into this equation. You know, just who knows what they're going to throw at you. So be very familiar here. Michaelis-Menten kinetics can be analyzed quantitatively. Yeah, so that's basically what we just said. Now, while the Michaelis-Menten kinetics curves are certainly useful, they're not exactly easy to read in the hyperbolic form, right? If we're looking at something like this, you know, granted, you know, the trends are what we're most interested in here, but even so, we need a better way to approach the numerical aspects of the reactions on these graphs, right? And that is where that's where our Lineweaver-Burke plots come into play. That is the point here, okay, of a Lineweaver-Burke plot. It is particularly useful when we get to the inhibitors and how the lines will differ. This gives us a linear relationship to work with. Yeah, so the other thing that's convenient about having a plot in this form is we can bring back some of that old high school math again to give us some really key information, right? You can use the y equals mx plus b, which I believe David went through in at the end of his last lecture, which we'll also be using a lot in the upcoming session on Monday. But like this y-intercept, for example, oh, no, I'm sorry, that's the x. This y-intercept, for example, which obviously is not represented in the Michaelis-Menten curve, can be identified on a Lineweaver-Burke plot. And that y-intercept is 1 over your V max. So lock these things into your mind, right? Y-intercept equals 1 over your V max. That should be like right in there, right in the memory bank, right? And it'll make figuring out the other aspects of this reaction much easier. You can bet there will be questions on the exam that will require you to employ this strategy, right? So what else do we have here? We have the x-intercept here. That x-intercept is representative of what? Anybody know? Well, it's right here.
-1 over km.
There you go. -1 over km. X-intercept equals -1 over km. Okay. And it's a matter of really just, you know, you should know basic reciprocal math at this point. We're not going to lecture on that. or go through derivations or the arithmetic aspects of the, for the sake of time, but you got to lock that in, that the x-intercept is -1 over km, and now you're equipped with another major value, So you have Vmax, you have Km, these are important. Substrate concentration is sometimes given to you, sometimes you got to figure it out. Eventually, we're going to talk about how the comparison of curves in the presence of inhibitors, right? If you have this, for example, or if you have this, for example, these mean different things. And we're going to go through that in terms of the inhibitors. I think that's what you guys are really talking about. How do I know what's what? The way this line here changes, the way that this line changes is going to help you determine what kind of inhibitor we have and how to identify the changes in Vmax and Km, because you got to know, okay, like an uncompetitive inhibitor does this to the Km and this to the Vmax. Okay, I'm going to keep it simple for now so we don't get too too granular. I don't want to hit you with too much info, and we're going to try to wrap this up pretty soon, but let's move forward. The general rate constant, kcat. A couple of you also reached out to me about this. Dr. Peterson included, or hang on, nope. Where are we? Let's go to kcat. There it is. So, okay. In our most optimal concentration of substrate, what is the turnover rate? That's what kcat is, the turnover rate in the reaction. And that's the key here. You probably won't need to calculate it, but you got to know what it means. You definitely got to know what kcat means, the turnover rate. So the general rate constant, kcat, describes the limiting rate of any enzyme catalyzed reaction at saturation. If one step in a multi-step reaction is clearly limiting, kcat equals the rate constant for that step. So if you only have a one-step reaction, your kcat is going to be, that's it, your limiting reagent. Do we all know what a limiting reactant is, or the rate limiting step, rather? Let me just put it into perspective really quick. It's the slowest step in a metabolic pathway or a series of chemical reactions, right? It's going to determine the overall rate of other reactions in the pathway, right? I mean, not necessarily irreversible, but in many cases, yes, the rate limiting step is irreversible. And we'll get more into that when we talk about glucose metabolism and carbohydrate metabolism. But it sounds like you have some familiarity already with rate limiting steps. But in an enzymatic reaction, the rate limiting step is generally the stage that requires the greatest activation energy or the transition state of highest free energy. Okay, it's the slowest part of the whole series of reactions. And because it's so slow, it's the gatekeeper. You're not going to move any faster in a reaction than the rate limiting step, hence the term rate limiting step. Now, in most cases, there's only going to be one rate limiting step, right? This is, oh boy, there we go. This is usually the case, okay? At least within the scope of this class and the pathways that we'll discuss. But when you introduce more than one step, things get a little bit more complex, okay? Many enzymes catalyze reactions with two or more substrates, right? So this slide says it all. Nearly 2/3 of all the enzymatic reactions have two substrates and two products, and that makes sense. An example, a group is transferred from one substrate to the other, or one substrate, redox reactions, oxidation reduction reactions, which are going to become a very big focus in future lectures, because especially when we start learning the long pathways, the complex pathways. But just keep this knowledge in mind. Sometimes enzymes catalyze reactions with two substrates. Sometimes it has three. It's a ternary complex, right? And substances or substrates can bind either randomly, as shown here, or they can be ordered, right? In a specific order. Here's step 1, step 2, and then so on. So you'd have enzyme substrate come together to make our enzyme substrate complex 1. You have the other substrate come in. Now you have enzyme substrate 1, substrate 2 complex, and they're all just coming in and making one big glob, right? The enzyme is gonna work its magic. Hang on a second. There we go. It's going to work its magic in this step, right? It's going to do the catalysis of the reaction. And now we have a glob, but with the products. Enzyme product 1, product 2. Then product 1 will dip out. And we have us a little bit of a smaller glob. And then these two will break up apart into these components. It's simple enough. You know, you look at it long enough and you analyze this slide, you'll get it. Okay. On the other hand, some enzyme reactions do not form a ternary complex, right? So sometimes the first substrate will be converted to the product and then dissociate before the second one comes in. Before we had them all coming in to make one big glob, sometimes no, sometimes it doesn't do that. Sometimes you have the first portion happen, right? You get your enzyme product 1, the product does its thing, and then the second part will come in. Like sometimes it's also ordered in that fashion. Be aware of these differences. They're not like, it's nothing crazy, but you know, definitely be aware of it. Steady state kinetic analysis of bi-substrate reactions. We mentioned these ternary complex and whatnot because it ties right into our Michaelis-Menten kinetics, which we're going to talk about. Michaelis-Menten steady state kinetics can distinguish between pathways that have a ternary intermediate and pathways that do not. That's kind of the big picture that we're talking about here. Graphs, and more specifically, the trends in those graphs. Like I said, these lines can tell you a whole lot about what's going on. And I know it's a little bit odd. It's kind of weird to just look at a graph with a bunch of random lines, right? And tell me about what's happening microscopically. Like, if you told me a year ago that I can look at this and tell you what's going on in a reaction, I would have laughed at you. But you know what? We're going to be able to, we're going to do that before the next exam. We're going to know exactly what happens because these lines can tell you a whole lot about what's going on, including whether or not you have a ternary or non-ternary complex forming. So these graphs are big, and that's the beauty of biochemistry. We can simplify something as complicated as all this, right? As all this nonsense that I just showed you, and we can make it something simple like that. Something that other biochemists will know what we're talking about when I give them this graph. Now, again, like on that note, let me just say, biochem is biochem, as we said earlier. In most cases, there's only one correct way to do things or approach them. So with that said, it doesn't matter where you get your info from as long as you get it. We host these review sessions. Dr. Peterson has her stuff. Can inhibitors play a role in forming a ternary complex or lack thereof? That's a great question, AM. Let me get some more information on that, okay? Because I want to give you an exact correct answer. Can inhibitors play a role in forming a ternary complex? Let me think about that. I'll get back to you. Dandy, I love it. Okay. Anyway, so you guys get the point. So over here, back on this slide, what are we looking at? If there's an intersection of multiple graphs, there's a ternary complex. That's how you know. It's that easy. If it's ordered or random, you can't really tell. That's different. But you can certainly tell that there's a ternary complex being formed. So if Dr. Peterson asks you, what is represented by this graph, and one of the answers is a ternary complex, you know, you might want to pick that one because, you know, that's what we're looking at. This intersection, the lines themselves are it doesn't matter as much as we'll see in the next slide. It's the intersection of the slides or of the lines that will tell us that we have a ternary complex going on. Now, do we have a ternary complex here? Who can tell me?
No.
Oh, thank you. No, we do not.
Nah.
Nah, no shot. Why? These are parallel. There's no intersection. Okay. In this case, we're probably looking at what? That ping pong or double displacement pathway, right? From up here. We're probably looking at something that does not form a ternary complex, something where the first substrate is converted to product, jumps off, and then the second substrate jumps in. Get these trends in your head, like it'll eventually stick very nicely once you do it enough times and have that inner dialogue with yourself. One of the inhibition plots looks exactly the same as a ternary plot. How do we tell the difference? Yes, that's actually a great question as well. I am gonna go ahead and hold off on that just because we're not going to touch inhibition just yet. I don't want to throw out too much information, but I will absolutely cover how you distinguish between, what you're looking at, because they're saying two different things. The inhibition plots are not representing individual, like the lines aren't a different reaction. They're just how the line would change, right? So let me just really quickly show this. Right, these lines are showing different parts of the same reaction, right? When we're looking at an inhibition plot, right, you have your XY axis. It should be Lineweaver-Burke. So this might be the original reaction by itself, uninhibited, but this may be while it is inhibited. So they're talking about kind of different things. I know they look very similar on a graph, but they're not. We're talking about the same line if you added an inhibitor versus if you have. Oh my, why does it keep doing this? Versus if you have no inhibitor. Okay, we're gonna get more into that. I'll make that much clearer in our next session, but they're two different things. Let's just keep running through. We talked about this, guys. We know that pH matters. It matters so much. We already talked about like ionization, and by now, especially after your protein lectures on charged amino acids, you should be familiar with the fact that pH has a notable impact on most, if not all, biological and biochemical processes. Right? It changes the whole charge of a protein, and you guys got to know how to do that. You get a sequence of 6 amino acids, you better know how to determine the charge of the entire complex. Okay, you're welcome, Fidan. Thank you. I hope I'm saying that right. I apologize, guys, if I'm saying your name right, incorrect. Just shoot me the phonetics in the chat or privately if you don't want to embarrass me in front of everyone. Hey, nice. All right, thank you. Okay. The point here that I'm trying to make is that certain enzymes will only work in certain pH environments, or rather, they'll only work optimally in certain pH environments. Why is this important? Well, I mean, obviously, if you have all of your body's enzymes firing off at full blast at all times, we'd be in a mess of trouble, right? Like the Krebs cycle, for example. I'm sure you guys are at least relatively familiar with Krebs cycle, right? In the forward reaction, you're breaking down glucose to make ATP, and in the reverse reaction, you're performing gluconeogenesis, or the process of making glucose from energy, right? They're two opposite reactions. So at the end of the day, running both of them at the same time would just be stupid. It's a futile cycle, which is another important word you guys are going to have to understand. In other words, you're going to build just to destroy again. So what's even the point? You're just wasting energy. There's a reason that, and pH is just one of the regulators of whether or not a reaction occurs or not. pH, it just has a major effect. So be aware of that. The pH range over which an enzyme undergoes changes in activity can provide a clue to the type of amino acid residue involved. Now, I'm not going to go reiterate any protein lectures right now. We will eventually, during the big review session. And of course, if you guys have questions, you can always feel free to ask me. But by now, I would hope that you started learning your one-letter representations and your amino acids, which ones are charged, which ones are not, polar, non-polar, right? Aromatic, which ones aren't. There's a lot of stuff you guys got to know. I believe you have to know the pKa's as well. I think we did, but You know, you guys have your work cut out. That's part of biochemistry's notorious difficulty. You know, you got to learn all of these different things. But that's where everything ties in. Remember the first lecture we talked about pH. Why did we talk about pH first? Well, because you know it's going to matter when we talk about proteins next, and when we talk about enzymes after that, because enzymes are mostly proteins, except for what? Ribozymes. Okay, these things all tie in, and I'm imploring you guys to take a look at these things, at all of these lectures from a global perspective. Okay, so we're going to stop here. All right, I'm going to stop right here because we're going to talk about inhibition next. A lot of these slides are kind of reiterating the same points. But for now, just for now, and you know, I'm really I'm loving how many people are here at this session. We got 18 people. This is excellent. You know, you guys are obviously taking control of your education. You're doing the best that you can to really step up to the plate. And I know a lot of us who are watching the recording, you know, you had other obligations to attend to, and you know, I'm not calling anybody out or anything, but I'm very happy to see everybody on their game like this, because you know, if I'm being completely honest, during my time last year, we were lucky if we had 2 or 3 people show up at a review session, you know. But I'm glad that these are helpful for you guys. So what I'm going to ask you, because there are so many people here present right now, I'm going to ask you, take a look at what we talked about, obviously become familiar with it, but also look at the inhibitor slides yourself. Look at what Dr. Peterson said. Do a couple of, maybe look at a YouTube video. There's like 6-minute ones out there. You know, they have nice, cool animations and pictures, and some of them are funny. You know, take a look. Yeah, don't pressure yourself to, oh, I must know this absolutely, I must perfectly know this by Monday. No, you don't have to do all that. Just become familiar. Get different perspectives of the same information. Okay, and then Monday I'm gonna run through. You know, I'll give you my take on this information on inhibitors, because that's going to be big. It's going to kind of pull everything together. And after, you know, after I get through the content portion, I'm gonna drill you guys with questions, man. You better come wearing your workout clothes, because we're gonna go to work. All right. So, you know, it'll be best for you if you come equipped with at least a decent amount of prior knowledge, so that we can tackle this, and so that you can get as much out of it as you can. Because the way the way we're structuring this is to get you guys the A that you're shooting for. Not everyone's gonna get it. I can guarantee you that. These are not easy exams. But by doing what you're doing now, attending these sessions, by taking a little bit of time in the car, sometimes in the car, I'm weird. When I take notes, I like to explain it back to myself using that Feynman technique I discussed. So I have just hours of me talking to myself like a crazy person. I have an hour commute every day to and from campus. You know, I could listen. I could blast the new Travis Scott or some Eminem, a little bit of Frank Sinatra. I could, and sometimes I do. But if I'm feeling good and I'm like, hey, you know what? Let's get ahead a little bit. I'll put on a recording. I'll just listen to myself talk, as vain as that might sound. You know, why not? I'm explaining it to myself. I'll pop on a YouTube video. I won't look at it, of course. Everyone drives safely, but I'll listen. You know, just here and there. Don't pressure yourself. Otherwise, you're gonna get stuck. You're not gonna do anything. You know, take a look, get familiar, and then we'll really drill these concepts into your mind on Monday. I'll give you some practice questions. We'll get you comfortable with your problem set that's due the next day. Okay. And then it's on you guys to really put in the work. Remember, an amateur practices until they get it right. A professional practices until they can't get it wrong. And that's what you got to do here. Are there any questions? Nothing at all? How do I stop sharing here? Stop. Okay. Where can we find my WhatsApp? So if you have any other questions, I'll tell you what, I'm going to just go ahead and post my number right into here. I would rather you limited your correspondences to WhatsApp, so I have everything in one place. But if you really are just having trouble with WhatsApp, just go ahead and shoot me a text. You know, just but do please before you reach out, let me know your name because I'm just seeing phone numbers and I would love to get to know you guys and your names and a little bit more about who I'm talking to. What time is the review on Monday? We're gonna shoot for 1. I'm gonna go ahead and I'm gonna send out a more detailed update in within the couple hours, and then you guys will have all the information you need. But I'll definitely send that out along with the Zoom link, and um I also have I'm gonna plug a USG event that we have going on. I'm the secretary for the student graduation or for the student graduate body, and we have a pretty cool event coming up for you first years. I believe this Thursday coming up where we're gonna try to acclimate you to the NYMC setting. We're gonna give you a few strategies on how to maximize your time here. You're going to hear some testimonials from second years like us, and we might try to get a couple med students who are in the program as well to just give you a little bit of insight. One of the things that I wish I had known when I was a first year is what do I expect, guys? I'm here. I have no idea about the NYMC atmosphere or the way things are done. I'm a brand new. I'm a little guppy in a big pond. So we're gonna try to help you guys out. We're gonna have some snacks. We're gonna have some fun dialogues and icebreakers. You can meet some new people, some new second years who are, much cooler than I am, and you get to associate with them and make some new friends and have an open, friendly dialogue among peers, but peers that are willing to help each other. So I'll send that out, and we'll be excited to see you come join us. I'll be there, of course, and it's on you guys. Enjoy your weekend. Thank you for joining me today and for listening to me yell into the mic all for the past hour and 20 minutes. And thank you very much. I'll be in touch.
A quick comment. So I just wanted to say that we do have the physio review on Monday as well. Oh no, actually, it's on Tuesday, never mind. Sorry.
Okay. I'm sorry. Can you repeat that? My bad. You broke up a little bit there.
No, I was saying for next week, I thought our physiology review was on Monday, but it's actually on Tuesday, so never mind. I thought the times overlap.
Okay. Yeah, and if there is ever a time issue, we can always go back and reschedule. I'm flexible. Thanks for pointing that out, though. You're welcome, everybody.
Sure
Thank you.
thing.
Yes, no problem at all. I'll see you guys soon.
Thanks.
You're welcome.